All rise! Hear ye, all rise! For the Honorable Judge Peter J. Wykes, the Court of Physics is now in session.
The jury may be seated. Now, Professor Sprott has been accused of breaking the laws of physics, and we intend on putting him on trial for his crimes today. Bring me Professor Sprott.
Welcome to the wonders of physics. Now, I have been accused of breaking the laws of physics, but it isn't true. And I've asked some of my trusted assistants to come and serve as expert witnesses. And I would like you to be the jury and decide whether I'm innocent or guilty.
Professor Sprott, you have been accused of breaking Newton's law of gravity in several demonstrations we saw you do. How do you plead? I'm
innocent, Your Honor. And if it pleases the court, I'd like to call my first witness. I call to the stand Dr. Stefficus. Please state your name and occupation.
I'm Fraulein Dr. Professor Stefficus Augustus Macmillan Winchester IV, and I am the authority on the laws of physics.
Now hold on, I'm the authority in this courtroom.
I think not, my good sir. Why, I understand equations both simple and quadratical.
Well, I know how to do that. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Huzzah!
And how then are you at integral and differential calculus?
Well, I'm a bit rusty.
How do you expect to command respect if you don't even know your maths? Now, I am an expert in conics and peculiarities parabolas.
Excuse me, could a witness please spell that?
Sure, T-H-A-T.
Thank you.
Well, I'd better hit the books. Please just give us your testimony.
Did you or did you not, on February 21st, 1988, see me do a demonstration in which a liquid crawled up the side of a beaker and over the rim?
I wasn't even born then.
And I wasn't born yesterday. Can you please tell us why that does not defy the law of gravity?
Sure. Let's take a look at my first exhibit. So normally when we deal with fluids, we deal with something like water, which I have here with a little bit of food coloring so the jury can see it better. So when I pour water from the top beaker to the bottom beaker, and I don't change the amount that I'm tilting the beaker, eventually the water is going to level off and stop pouring. We call water a Newtonian fluid, and here I have a non-Newtonian fluid, which we'll see will behave a little differently. So as I tilt the beaker, it's going to continue pouring out of the top one into the bottom one, even after the point where water would have stopped pouring. This is because this fluid, which is polyethylene oxide, is made up of long chains of molecules called polymers. And these polymers will continue to pull out even because of the chemical bonds that join the molecules together. We can see this with an actual chain here. So if I throw the chain over, it continues to fall out of the beaker, even though I'm not tilting the beaker at all. So with this exhibit, the bit of chain that was outside of the beaker weighed more than the loose bit of chain that was inside the beaker. So once it started falling, it just kept pulling the chain behind it and continued to cascade out. For my next exhibit, we'll look at the stack of cards, and we can make it look like it defies the law of gravity by going like this, and it looks like the cards should fall over, but they don't. To understand what's going on, let's take a look at one card. So with one card, as long as most of the mass is supported by the table, the card won't topple over. But as soon as we go past that halfway point, the card falls off the edge. So when I put it in an arch, It looked like it should topple over, but actually our intuition was just tricking us, and most of the mass was still supported, so it stayed on the table. And that's actually the St. Louis arch. The two halves don't need to lean against each other. They can stand up independently. For my next exhibit, we call this the faster than G stick.
Faster than cheese? I like cheese. You know, Gouda, Limburger, Kobe.
No, not cheese.
Oh.
G, like gravity. So I'll explain why it's called that later, but we have this plank of wood, a ball balanced on top of a golf tee, and this rod that's supporting the wood. So if I remove the rod, who thinks the ball's going to land in the cup? Raise your hand. Who thinks it's going to land somewhere else? Okay, get ready. We'll see what happens. So it landed in the cup, which is really cool. But it seems a little counterintuitive because Newton's laws tell us that all objects are supposed to fall at the same rate. But here we have the force from the hinge in addition to the force from gravity. So actually only one point along the plank, about here, is going to fall at the same rate that the ball falls. And because this plank is a rigid object, everything that's past here has to fall faster, and that's how the ball can land inside the cup, because the cup is falling faster than the ball. Now for my last exhibit, I'd like the members of the jury to remember Jack and Jill, and did they fall up or down the hill with their pail of water? Down, right. So here I have this double cone shape, and I have this type of little hill. So if I put the cone in the middle of the hill, who thinks it's going to roll this way? Raise your hand. Who thinks it's going to roll back toward me? Okay, let's see what happens. So it rolls this way. Let's put it at the bottom and see what happens. So it still rolls this way. And that's because we kind of have a trick hill here. So this hill is made up of two rails, and at the bottom the rails are really close together, and as it moves toward the top of the hill, the rails split apart. That means that at the bottom of the hill, the cone is higher off the surface of the table than it is at the top of the hill. So the cone is still moving downward and is moving closer to the surface of the table, so it is still going with gravity.
Thank you, Dr. Stefakis.
Thank you.
I'll take your evidence into consideration. Now, Professor Sprott, you have also been accused of making water boil by cooling it, which is an obvious violation of the laws of thermodynamics. How do you plead?
I'm completely and totally innocent, Your Honor, and I would like to call my next witness to explain why. I call to the stand Ed Leonard. Please just state your name and occupation.
Ed Leonard's the name, but all the lion tamers and snake charmers call me Rex. That's right, Rex, because I'm the king of the carnival. My physics exhibits will astound you under my big top tent.
Excuse me, would witness please stop being so annoying?
Sure, I'll be quiet as a mouse, meek as a lamb, and sleepy as a kitty.
Thank goodness.
Well, Ed, you've been called here to give testimony about some of Professor Sprott's thermodynamics demonstrations.
Professor Sprott, the cat in the hat, the man in the prison-striped tuxedo today. Step right up, folks, and see the greatest show on earth.
Well, now, Ed, that's all very nice of you to say, but did you, on February 19th, 2006, see me do a demonstration in which I boiled water using ice?
Well, now you mentioned an old chap that does sound somewhat familiar. But it's not as fun as boiling a trapeze artist in midair.
Oh, wait a minute. Forget the trapeze. Just continue on with your exhibit.
All right. So I have here a flask of water. And underneath my flask, I have a fire. Now, if I let the fire heat the flask for a long time, what will happen to the water? Yell it out. It'll boil. What temperature does water boil at? Just yell it out. Absolutely. So 100 Celsius, 212 Fahrenheit. Kelvin? Anyone? You right there in the purple. She's Mom. Anybody else? It's 373 Kelvin, okay? So, we're getting this water up to a boil, and you can see that it's starting to. Now, water, we use it so often that we've named the phases of it. So what do we call solid water? What do we call gaseous water? What do we call liquid water? Very clever jury. Very clever jury. Okay, so we've got this water boiling, and now I'm going to close it off. So now the water vapor can't escape. Okay, we're going to let it cool down for a moment now. So water boils at 100 degrees Celsius. That means that the water that is boiling here is 100 degrees, and to get hotter, it has to actually transition into water vapor. So now that we've stopped boiling, we've got water vapor on the inside, and it's trapped, and I'm going to add ice to this top of the flask. And what that ice will do is come into contact with the flask, which is in contact with the water vapor. That water vapor will then cool and condense, reducing the pressure inside the flask. And we're going to give it a moment here. You can see it's starting to get pretty excited. And you'll notice that now I've got a boil that's starting up again, even though my heat is off, and it has been off for a while. This is because you can choose different points in phase space. You can choose different pressures and temperatures, and you can change the boiling temperature of water that way if you look very carefully up here. So water's boiling with ice. Very fine. Now I would even go so far as to say you can go to extreme pressures. You can make room temperature water freeze.
Now wait a minute. Freezing water by room temperature? That doesn't sound right.
You didn't swear me in, Your Honor, but maybe you should have. So here we are with another flask of water, and attached to this, that's still boiling, by the way. Attached to this flask of water, I have a vacuum pump. Now you can see the pressure inside this right now is about 76 centimeters of mercury. This is a basic atmospheric pressure. But if I turn on the vacuum pump, we can see that the pressure drops down very quickly, and now the water starts to boil. Now this water wasn't being heated at all. So it's boiling, and boiling takes energy. But the only energy this water has to give off right now is its thermal energy. And if you remove thermal energy from water, what do you do to it?
Freeze it!
You freeze it! And now I have a block of ice.
Now hold on, this reminds me of another charge against Professor Sprott. He's been accused of making a cannon without explosives. What say you to that?
Well, I don't like explosives much, mister. Ever since that cannon incident back in '05. But we start talking about cannons, you think about what? You think about explosions, you think about steam, maybe you think about electromagnetic energy. You don't need to have explosions anymore. We've got more better technology. So what I'm going to use is liquid nitrogen, because it's one of my favorite things. Here I've got a couple ounces of it. I'm going to put it into a small tube. Now, inside the small tube, while the tube is open, it is completely harmless. However, when you boil a liquid, it expands by a huge factor. Can anybody tell me that factor? This kid knows his stuff, 1,000. Okay? So if I try to trap 1,000 times a couple ounces in here with my hammer, he's going to do it. And shake it. Woo! I hope that some young juror will see me after court today with a gift for me. I love presents. So I believe that Professor Sprott is innocent, and if it pleases the court, I'd like to start talking about my new take on Cirque du Soleil. It's actually...
Now wait a minute. Nothing about you pleases this court. Pack up your circus tent, take your tap dancing elephants with you. The witness is now dismissed.
Well, that's your loss. Everybody else is going to experience tightrope tap dancing elephants wearing party hats. The idea of it.
Now, Professor Sprott, another charge against you is that you have been able to make sounds that cannot be heard. How do you plead?
Once again, Your Honor, I'm totally innocent. And if it pleases the court, I'd like to call my next witness to explain why. I call to the stand Akire Trestrail. Please state your name and occupation.
I am Akire Trestrail, and I keep these streets safe for physics.
Is that your occupation?
Well, it's more of a hobby. Me and my crime-fighting dog, Sir Isaac, make sure that no one breaks the laws of physics.
And how do you do that?
Well, I've got my trusty utility belt, ultrasonic cleaner, transimpedance amplifier, sonic screwdriver, and of course, Isaac always helps out with his magneto-optical trap.
Excuse me, would witness please repeat that?
Sure. that.
Thank you. Thank you.
Now, have you saved any physicists from certain doom?
Recently, I heard my Doppler 1 in science activate. Isaac and I suited up. I readied my Boson-mobile, sure that the evil Dr. Schrödinger was up to a terrible crime spree.
And was he?
No, it turned out just to be a cat in a box. But Isaac was still pretty helpful, though. Where is Isaac? There he is. Now, I bet many of you are wondering how I called Sir Isaac without making a song, the same charge that Professor Sprott has been accused of. Well, the truth is, I did make a song. To know what I mean, you must first understand what sound is. What we call sound is just a fluctuation of high and low air pressures. How quickly they fluctuate is called frequency. So dogs can hear a much higher frequency or many more fluctuations than can humans. If you look at a range of hearing chart, you'd see the dogs have indeed a much higher range of hearing than humans can. To show what I mean, we can visualize what a sound wave looks like using an oscilloscope. Let's see what it looks like. So I used a tuning fork which produces songs in the audible range. The peaks of the sound, as you can see again, show where the air pressure is high, and the valleys showed where the pressure was low. How quickly, oh, I already said that, sorry, never mind. Let's see what the dog whistle looks like. Oh, sorry, Isaac. So if you notice, there were many more fluctuations with the dog whistle, again, meaning a much higher frequency. Okay, so I have an exhibit to show what I mean. I'm going to produce a sound wave. Raise your hand if you can hear the frequency. I'm going to vary the frequency up and down, and you put your hands down when you can no longer hear the sound. So let's hope this one works. Okay, so we can all hear this high frequency. Let's turn it down a little bit. Okay, we can all hear low frequencies. Let's go even higher now. Okay, put your hands down if you can no longer hear it. We can all hear these high frequencies. Let's go even higher. Even higher. Okay, some hands are coming down. Even higher. Okay. So it's interesting to note that the younger members of the jury kept their hands up the longest. As it turns out, as you age, the range at which you can hear starts to decrease, allowing the younger members of the jury to hear much higher frequencies. All right. Now that we all are familiar with sound, would you like to see yet an even cooler exhibit? Yeah. Let's cross our fingers that it works. So I have here another ultrasonic beam that I can produce. I'm going to reflect it at this reflector. That's going to set up what's called a standing wave, meaning the high pressure regions of the air would remain fixed in space as well as the low pressure regions. I will use that to suspend this piece of styrofoam. Let's see how many we can get. So what's happening is the styrofoam got caught in the low pressure regions with the two other high pressure regions pushing it towards the low pressure region where it became stuck. Uh-oh, that sounds like trouble. I better go see what it is. Last time, Isaac found Timmy stuck in a gravity well.
Now, Professor Sprott, you have also been accused of breaking Ohm's law. How do you plead?
I'm innocent. You can't break a law that's not really a law.
Not a law? You, sir, are flirting with contempt of court.
Not at all, Your Honor. And I'd like to call my next witness to explain why. I call to the stand Mike Randall.
Kitty.
Mr. Randall, please just state your name and occupation.
I'm Mad Mike Randall. I teach mad science to children.
You want him as a witness? And why are you wearing a cage on your head?
Excuse me, is that 1R or 5? Okay, that sounds like 5.
Mr. Randall, please stop fooling around and explain to the jury why Ohm's law is not really a law.
Well, to understand Ohm's law, we've got to understand some other things first. The world is made out of stuff. Scientists like me call stuff matter. If you take any piece of matter and you break it into smaller and smaller pieces, you'll eventually end up with some little teeny tiny things that sound like a boy's name. What would those be? Just shout it out. What? Atoms. Very good. Very good. Atoms. But atoms are made of even tinier things. If you could somehow look inside of an atom, you'd find some really tiny things in there. Starts with the letter E. Starts with the letter E. Electrons. Excellent. Usually when we talk about electricity, we're talking about the movement energy of those little electrons. Ohm's law explains the relationship between how hard those electrons are being pushed, that's called voltage, or V, how many electrons go by in a certain amount of time, that's called current, or I, and how much the material that the electrons are moving through resists that movement. That's called resistance, or R. Resistance is futile. Anyway, Ohm's law demands that the relationship between voltage and current be linear. For example, if I double the voltage, in this case from 4.5 to 9 volts, the current also doubles, in this case from 100 to 200 milliamps. However, that's not always the case. For example, when you electrocute a pickle. I love electrocuting pickles. They sizzle. The smell is horrible. But that's the best part. Did you see it light up? Yeah, weird, huh? But that's not the weirdest part. Did you notice that the pickle flickered? If that electricity flowing through the pickle had been following Ohm's law, that light would have been constant and even, but it wasn't. That's because salt in the pickle juice creates something called sodium and chlorine ions. Now, ions are atoms that are either missing electrons or have extra electrons. It's the ions that are carrying the electric current, not electrons. And it turns out that electric currents in ionic solutions often do not follow Ohm's law. Now I have another example for you, but I'm going to need someone from the jury to help me out with this. Someone from the jury to help me out. Someone, how about you right here? Come up here. Quickly. What's your name?
Kristen.
Kristen. Kristen, how well do you know your states of matter? Well, let's find out. These ping pong balls represent atoms. Hold that up so the audience can see it. Nice and high. Now just kind of shake it back and forth. Notice not much happens here. The atoms are pretty well tightly packed and pretty tightly connected. What state of matter would this be?
Solid.
Yes, this would be called a solid. Okay, in this case, the atoms are more loosely connected. Just rock that back and forth. Notice how that they'll flow. They'll kind of take on the shape of the container. What state of matter would this be?
Liquid.
This, of course, would be a liquid. Now, in this case, the atoms are not really connected at all. They're free to go wherever they want. Shake it up and down really hard. Yes, I can actually fill up the entire container. They'll take up as much space as we give them. What state of matter would this be? Of course, this is a gas. Kristen, you did a great job. Let's give her a big round of applause. Thank you very much. Go ahead and sit down. Oh, wait, there's a state of matter I forgot about. It's this one. It's plasma. If you take any matter and you hit it with extreme heat or extreme voltage, you can actually rip the electrons off the atoms. That's what a plasma is. It's a mixture of these free-floating electrons and atoms that are missing electrons. Those are called ions, remember? Electricity flowing through a plasma also does not follow Ohm's law. In a plasma, the electrons and the ions are carrying the electric current, and as they're moving around, they create magnetic fields which affect how they move. Bottom line, with all that extra stuff going on, electricity flowing through a plasma simply does not follow Ohm's law. Would you like to see what I can do with the plasma? Yeah. This is very loud, especially for you in the front rows. Cover your ears. This is called a musical Tesla coil, named after famous inventor Nikola Tesla. This makes plasma using high voltage electricity. Would you like to see another one? Yeah! Cover your ears. Clearly that plasma is very hot. As that electricity is flowing through the air, the plasma makes the air around it expand. We can turn the electricity on and off hundreds of times a second, which makes the air expand hundreds of times a second, making the sound waves that you can hear. We control the frequency or the pitch of that sound simply by how often we turn the electricity on and off.
Okay, I think we get the point. Now, will somebody please put this guy back in his cage?
Oh, Tweety, no!
Now, Professor Sprott, you have also been accused of using magnets to push on electrons and transferring electrical power without using wires. How do you plead?
Once again, I'm innocent, Your Honor. There's no law of physics that prevents that, and I'd like to call my next witness to explain why. I call to the stand Andrew Saltzman.
Let's some science here. Let's flip some switches and pour some of this and
Andrew, can you stop fooling around over there and take the witness stand?
Oh my, yes, I'm a witness. To the stand.
Please state your name and occupation.
I am Andrew Saltzman, master of electromagnetic waves, inventor of this and that.
Excuse me, would witness please say that more slowly?
That.
Thank you.
You're welcome.
Now, Professor Sprott, you have been accused of bending the path of moving electrons without actually pushing on them, thus violating Newton's first law. How do you plead?
I'm innocent, Your Honor. There is a force, and it's called the Lorentz force. Andrew, would you explain?
Indeed. Over here, we have a device to demonstrate the effects of said Lorentz force. Within this glass globe, we have a device which launches a beam of electrons downward, as seen here. This beam of electrons passes through a very low pressure gas, causing it to glow, thus allowing you to see the path which the electrons take. Now, from Newton's laws, we know that anything in motion remains in motion in a straight line. Thus, the beam of electrons moves straight downward. But watch what happens when we turn on a magnetic field by running current through these two coils of wire. The beam begins to bend. But even more interestingly, watch what happens when we increase the magnetic field further. The beam bends into a circle. This is because the Lorentz force is a force which acts at right angles to the path of a beam of moving charged particles. Thus, as the path of the beam bends, the force bends as well, always pointing towards the center, thus allowing the electron beam to circle around and around as seen here. Another fascinating demonstration involves this disk of superconducting material. First, we will cool the disk down to cryogenic temperatures with liquid nitrogen, allowing it to become superconducting. A superconductor, unlike a normal conductor, has no resistance. Thus, any current that begins to flow in the disk continues to flow unimpeded. Watch what happens when we bring this small magnet near the disk's surface. The magnet levitates above the surface of the disk. This is because as we bring the magnet near the disk's surface, the increasing magnetic field drives currents in the disk's surface. These currents trap the magnetic field lines from the magnet, thus suspending it in space, levitating above the disk. And speaking of magnets, what have we here? A giant electromagnet. With this electromagnet, we can generate a very powerful changing magnetic field by running current through this coil of wire. Now, a rapidly changing magnetic field generates an electric field which circles around it. This electric field can be used to transfer power without wires. Watch as we turn on this magnet and bring this second coil of wire nearby. The electric field drives current through the second coil of wire and drives it through this stainless steel rod attached to the front. The flowing current heats the rod white hot. Behold. But that's not the only way to transfer power without wires. Here we have a microwave oven, and in it, a fluorescent light bulb. This fluorescent light bulb contains a low-pressure gas. Normally, when you plug it into a light socket, the voltage from the light socket drives current through the gas, heating it into a plasma, thus causing the fluorescent light bulb to turn on. But the radio wave in a microwave oven also has a rapidly changing electric field. This electric field can also excite the gas in this fluorescent light bulb into a plasma. Observe as we put it in the microwave and turn it on. And one more demonstration. Let's take this thin piece of metal foil and put it in the microwave oven.
Now wait a minute, Andrew. Is this going to be safe?
Safe? Not really, but I'm going to do it anyway. Watch what happens. The electric field from the radio wave drives currents in the surface of the foil, causing it to arc and spark and catch fire.
Well, thank you for your evidence, Andrew. I will take it into consideration.
You're welcome. And I hope you've enjoyed my electrifying testimony.
Now, Professor Sprott, you have also been accused of using magnets to attract and repel aluminum and copper, which we all know are not magnetic materials. How do you plead?
I'm innocent, Your Honor, and I'd like to call my next witness to explain why. I call to the stand Michael Winokur. Please state your name and occupation.
Michael Winokur, scientist by day, but because of my magnetic personality, physics party candidate by night.
And in your capacity as a physicist, have you seen me do a demonstration in which I levitated an aluminum ball using an electromagnet?
Of course, an excellent demonstration.
And does that demonstration violate any laws of physics?
Laws? Laws, you say? Did you know that a vote for me is a vote for Ampere's law and magnetic order?
Well, that's an excellent platform, but we really want to know about the physics.
Nothing better. I love babies. I love Ampere's law, and I love physics.
Excuse me, could you say that a little louder?
That?
Thank you.
Well, you have my vote.
All right, Professor Sprott, that's enough. Have a seat. No more of these electoral shenanigans in my courtroom. Please, show us what you know about magnetism.
No problem. Like I said, I have a magnetic personality. Ampere's law relates electrical currents to magnetic fields. And this I can demonstrate in Exhibit A, which is on the table here. Now, part of the exhibit is this little item. It's an ordinary compass, which is just a magnetic needle on top of a little pin. How many of the jury members have used a compass before? Ooh, very good. Well, then, let's see. You will know that a magnetic compass usually points to magnetic north. But this one has somehow had its polarity adjusted, so this one's actually pointing to magnetic south, but close enough for the exhibit. Now, in this exhibit, you will see that we have a wire here, and a copper wire, and copper is an electrical conductor. And when I turn this switch, I will send 20 amps amperes of electrical current down the wire and out, and we'll see which way the compass points. If you follow, watch here, see it doesn't point, it points out a circle of the magnetic field around the wire. It's called the Ørsted effect, and it shows Ampere's law in action. But in fact, we don't have to be restricted to just electrical currents. We can see the magnetic field in a variety of situations. I call the jury's attention to Exhibit B. In this exhibit, I have a container with a hole in it, but in the container itself, it's sealed and has oil and very, very fine iron particles, which are a little bit magnetic. And I will shake this up in order to disperse these particles. I'll turn the light on. Let's get the light on. There we go. And you can see that the particles are fairly evenly dispersed. But now I'll take an ordinary bar magnet with the North Pole and the South Pole and stick it in the hole, and you can see what happens. Watch on the screen. Do you see that? Yes, the magnetic particles follow the magnetic field produced by the magnet, and where the magnetic field is strongest at the poles, you see the highest concentration of magnetic particles.
Well, I do see circles there, but what does this have to do with the demonstrations you saw me do?
Oh, that's the easy part. If you'd been following my campaign, you would know that many things can be made to follow magnetic fields, even though they're invisible. I draw the jury's attention to a very strong magnet and Exhibit C. In this flask, we have a fluid. It's called a magnetic fluid. And what it is very, very, very fine magnetic particles suspended in a fairly thick oil. And I don't even have to get the magnet close to get the oil to follow the magnet. Watch carefully as I swirl it around. And if I go close, you see a lovely decorative pattern. It sort of looks like a coneflower center. And that makes me think of spring, and hopefully it'll be here soon, given the weather outside. But that's only half the story. The forces there were pretty modest. But in fact, we can use these laws of physics to make much, much stronger forces, and for that I will need a new exhibit, Exhibit E, and that's over here. Underneath, down at the bottom, we have an orange can. It's a device that stores electrons. We call those devices capacitors. And in this capacitor, when I push this button, we will fill it with electrons. Millions and billions, and I don't know how many, but lots of electrons. And it will be at very, very, very high voltage, a large push, if you will. And when I release the button, it will send all of those electrons through this coil loop and back down, creating a very, very strong and quickly changing current. And to sort of show you the effect and how it can be made to act on a metallic object, we have an aluminum can, which we will induce a current in this can. That will induce create a magnetic field, and you'll see the result of the interaction by putting the can inside here. Now, this is a very loud demonstration, so you really should cover your ears. And you can follow along because there's a meter here. Each 10 corresponds to 1,000 volts. And when we hit 5,000 volts, I'll let go of the button. So that's now at 2,000 volts, at 3,000 volts. Oh, it's moving up. 4,000 volts. Pay close attention. I'm almost to the point. It takes a little longer at the end. I think we're just about there. Close enough for physics. Ready? So I can use this effect to crush my opponents. But we don't have to use this exhibit in exactly the same way. We can adjust it slightly and use a second can and put it like this and see how far we launch it out into the audience. Shall we try that? Okay. Here we go again. 1,000. 2,000, 3,000, 4,000, almost there. Good. You can pass it around. We call this kicking the can in political speak. Wow, that was fun. Now I really want to draw your attention to my final exhibit, Exhibit F. This is the exact demonstration that my esteemed colleague, Professor Sprott, is accused of performing. This is very similar to our previous exhibits, but there's a slight twist. Rather than having a direct current that only goes one way, in fact, we have two magnets, two electromagnets, and we'll be sending the current back and forth about 60 times a second. And that will create both an attractive and a repulsive force, and that effect will set up, again, a current in this aluminum can, which will create a magnetic field where there will be an interaction between the two, and we will, like magic, be able to suspend this can in midair. Are you ready for this?
Yeah!
So you can hear the hum. That means the current is working. And you can see it sort of works here, but it won't be stable because this is at an unstable equilibrium. But if I go in between the two cans, now that's where the stable equilibrium is, and I can give it a spin. And there it is. And if we turn off the power, of course, down it goes.
Well, thank you, Mr. Winokur. I will take your evidence into consideration.
Great. I have another political meeting to attend, so I'll have to give you a break.
Now, as Professor Sprott's next witness, I am going to call one of his co-conspirators to the stand who has been caught bending light with Professor Sprott, Mr. Marty Lichtman.
You know, I was just on the way to laundromat to do some, money laundering. I was so rudely interrupted by this trial. So, here, if you would hold my loot for me. I mean, not loot. I mean, tax-deductible contributions to the wonders of physics. But I didn't see nothing.
Well, I haven't asked you any questions yet.
Well, good, because I ain't saying nothing.
You will use proper grammar in this courtroom.
Oh, but for what? This ain't the wonders of English.
I will hold you in contempt.
Huh, well, I've never been to contempt. Is it nice this time of year?
Now I'm angry.
Well, hello, Angry. Very pleased to meet you.
If you're not careful, you'll go to jail for the rest of the year.
Oh, well, seeing as this here, 2015, is the International Year of Light, that will be, a very light sentence. A light year, if you will.
Now look here. We have evidence that you have conspired to violate the laws of physics with Professor Sprott. And if you don't cooperate, you'll find yourself in jail.
I have been trying to find myself. Oh, I'm right here, so no need for the jail.
Now look here. On February 15th, 1992, you were seen to bend light. And as we all know, light travels in straight lines.
No, but wait a minute. I can bend light using a fiber optic cable.
Aha, so you admit your guilt.
Ah, you and your tricks. No, it ain't guilt. It's physics. Come on, I'll show you. Exhibit A. We have here a laser beam. If I turn this on, you see it appears on the screen over there. Now, I can show you with a bit of fog that this laser beam is propagating straight and directly as you say it should.
Hold on. I object. You know, first of all, there's these stinky pickles over here, and now you're spraying fog all over the place.
You know, your perm seems to be drooping a little bit, so let me help stiffen that up for you. But anyway, this laser beam is propagating straight, as light beams do. However, if I take this fiber optic tube, which is essentially just a dense piece of plastic that has been curled up all spiral-like, and if I put this into the path of the laser beam, now you can see that the beam goes in, but it reflects off the edges, and it propagates around that spiral, bouncing inside. We call that total internal reflection. And in fact, the direction of the laser beam does change. It went in that way, and it comes out that way. But I don't even need no fancy plastic in order to do this. Well, yeah, let's say I just use some ordinary water. H2O. Exhibit B, Your Honor. I have here a large tank of water. Now, on the back here, we have a window and a laser beam. I can shine the laser into the water. And on the front, there's another window where the laser can come out. And this one has a valve that I can open up and let the water out. But I won't do it here because I don't want to get the members of the jury wet because I may need their sympathy at a later date, you know? So let's position it over here. And if I turn this on, you can see the laser is going in and ending up on the screen over there. So once again, propagating straight across the courtroom, all the way across. Now, let's see what happens if I open up this valve. In 3, 2, 1, go. Now you can see the laser is no longer propagating across the courtroom. It is not on the screen over there. Instead, it is coming down through the water, down into the trough. And you know, maybe we just make this a little more dramatic with some liquid nitrogen. Why not?
You know, that's just not right. That's an abomination to nature.
Oh, no, nature don't mind none. Ain't never seen a rainbow?
Well, I don't get out much.
Oh, well, that's too bad. Now you're making me feel bad for you. Well, yesterday being Valentine's Day and all. But let me make you a rainbow then. How about that? A little sympathy for the judicial system here. So I have here a nice piece of glass. I got it at a jewelry store downtown, you know, 5-finger discount, know what I'm saying? But this is the same type of prism, a triangular piece of glass that old Ike Newton used when he was doing his explorations of the properties of light and color. So I'll do what Ike Newton did, and I'll turn on some white light. I put it into the prism. It's going this way towards the members of the jury, but it comes out that way. It is bending, but you also notice that each color bends a different amount, thereby refracting out into the rainbow, or the optical spectrum, as we call it.
Okay, so you can use some material to bend light, but that must violate the law of physics somehow to do so just in air.
You like the stars, mister?
Oh, sure. I'm a big fan of George Clooney. He's dreamy.
You know, you got wax between your ears and nothing else. Not the movie stars, the stars in the sky. You know how they twinkle? No, you don't. But these kids, you know how they twinkle? Yeah, okay. Well, why does that happen? Let us investigate that. Exhibit D, Your Honor. Once again, we used our laser beam appearing on the screen there. That is now our simulated star, and you can see it's quite stable, not twinkling at all. I'm not shaking the table or the laser beam, and as we reminded you before, it is propagating nice and straight. But what would happen if I turn on, say, a gas burner? Just light this, and I will take this over here.
Oh, wait a minute. No, keep the flame so away from my beard.
So let's hold this gas burner directly underneath the propagation path of the beam. And we may perhaps want the lights a bit lower. But you can see that the star up on the screen there is now twinkling back and forth, jumping all around. Why is this happening? Well, this is happening because the exhaust coming out of this gas flame is turbulent. That means it has areas of high and low density. And when the light goes into the high and low density areas, it bends different amounts. The same thing happens when starlight comes to us through the turbulent atmosphere. The weather's making that air move around, and the areas of high and low density cause the starlight to move back and forth, making it appear to twinkle to our eye. And if I take this away, you can see once again, it is nice and stable.
All right, so light can bend, and that's perfectly allowed by the laws of physics.
Yeah.
But you've also been caught changing the speed of light, and that's a horrendous crime.
Oh, well, and you're in on the heist, buddy. We've gone and done changed the speed of light 3 or 4 times in the last 5 minutes.
How dare you accuse me?
Oh, well, I ain't gonna judge you.
That's my job.
Exactly. But no, let me let you in on a little secret. So you know the speed of light, it's a constant in a vacuum. However, when light goes through some material, and that could be a solid material like the fiber optic tube or just air, it interacts with the atoms, and that interaction takes some time, thereby slowing down the beam of light. And it is that slowing down which is related to the fact that the light beams do bend. However, that speed of light in a vacuum is a very important constant in physics. I'm myself always forgetting what it is. Does anyone remember what is the speed of light? Shout it out.
Isn't that like 7 million miles an hour?
It's not quite that number, but so maybe we should measure it, and then we can figure it out, right? And then we would know. So here at the Wonders of Physics, let us do some scientific experimentation, and then we will know for sure. That is the best way to determine a thing. So I happen to have a scientific apparatus here, and would you like to come down and perhaps assist me with this? So this device, what is your name?
Ethan.
Ethan. So this device, we have a small fiber optic cable. Now this is very similar to that larger fiber optic tube, except it's small and it's short and I can bend it easily. So when I put it in here, light goes in one end, and you see now light coming out the other end? Okay. Now if I put this into my device here, what happens is you see on the oscilloscope here, and the members of the jury can see on the screen, we see two peaks. The one on the top is when the light pulse starts. And the one on the bottom, the blue trace, that is when the light pulse is received at the other end. But it's very difficult to tell the difference between the two. They appear nearly simultaneous. And so it's hard to tell from that how fast light is. In order to demonstrate that confusion, let's see how long it takes you to go this far. Okay, so you stand right here. That's the start line. Now you're going to go to the end of this when I say go. Wait till I say go. Okay. Okay, because we got to do this scientific like. All right. On your marks, get set, go. But now it was too fast. I was way too fast, so I can't count that fast, and I don't know how fast you were going. And same goes for the light. I can't tell from that how fast it was going. Luckily, I have here a much longer fiber optic cable. So let's see how long it takes. First, we'll see how long this is, then we'll see how long it takes you to go this distance, and then we'll see how long it takes light to go this distance. A little bit of a race. Now, if the accused will please help me out, take this to the other end of the courtroom, and we will get a nice measurement of the distance. Now I have both free ends here, so the light will go in, down to where Professor Sprott is, and back up this way. Okay, I'd say that's exactly 30 meters. All right, so let's put this aside for the time being. I have a very calibrated eye, you know. And we're going to have you run that distance and back in time, how long it takes you. Oh, but I seem to have forgotten my watch. Does anyone in the audience have a watch that I perhaps could borrow? Ah, yes, that is a very fine timepiece. Thank you very much. And I'd like to remind you that thank you, all contributions to the wonders of physics are tax deductible. So now we will time you, all right, to Professor Sprott and back. On your mark, get set, go. 1, 2, 3, 4, 5, 6, 7, 8. Okay, between 7 and 8 seconds. So that's like about exactly 4 meters per second. 30 meters divided by 7 or 8 comes out to about 4. Okay. I would like the members of the jury to note that I have returned this man's watch. I do still, however, have his wallet. So, Ethan, now we need to do the same race with light so we can see how fast the light goes. All right, so let us take one end of our fiber optic cable and put it in here. And now, you can see the light's coming out of there, yes? All right, so that light is going all the way down to Professor Sprott and all the way back. And when we put this into our detector, we now see on the oscilloscope the blue trace is later than before. So the progression of time goes from left to right on the oscilloscope there. And it appears that the trace has been delayed by about 1 large division on the grid there. If you look at the bottom, you see what it says there? 100 ns. Now that stands for 100 nanoseconds. So what we have here is the light is going 30 meters in 100 nanoseconds. So quick, how fast is that? Oh, I got it first. It's 300 million meters per second. 30 meters divided by 100 nanoseconds. 300 million meters per second. Wow. So, okay, wait, so you went 4 meters per second, and the light went 300 million meters per second. So, okay, so I guess the light won, unfortunately. But you came real close. So thank you very much for helping us. Wowza. Wowza. 300 million meters per second. Oh, or that in imperial units, 186,000 miles per second. That is real fast. I sure wish I could get away from a heist that fast, you know what I'm saying? Speaking of which, being in this courtroom is making me a little bit nervous, so I think I'm going to make like a light beam and propagate.
Now, Professor Sprott, I have seen all the evidence, and I am ready for your closing arguments.
Well, I hope the jury has been convinced that I've not broken the laws of physics. In fact, it's impossible to break the laws of physics. Unlike the laws that our legislators pass and the judges and juries debate, the laws of physics are the same everywhere in the universe and for all time. Now, every law has a regime in which it operates, and we have to be careful not to apply it where it doesn't apply. And also, every now and then, we're able to find a more general law that explains a wider range of phenomena. But the laws of physics cannot be broken. And so I hope you, the jury, will find me innocent of these charges so that I can continue to do these shows for many years to come.
Has the jury reached a verdict? Yes. All those that think that Professor Sprott is innocent of these charges respond by saying aye. Aye. All those that think that Professor Sprott is guilty of these charges respond by saying no. Well, I'm happy to say that the eyes are above the nose. Court is dismissed.
Well, thank you for that lesson in anatomy, but I am pleased that the majority of you have considered that I'm innocent of these charges, and those of you who voted no, don't bother to come back next year. But with your generous support to the Wonders of Physics Fund, I do intend to continue doing these presentations for many years to come. Now I'd like to make my triumphant exit by doing one last demonstration for you. For 32 years, we put on these shows, and almost every show has ended by making a cloud. And I have an apparatus here that allows us to do that. It's a container with 25 liters of liquid nitrogen, the same liquid nitrogen you've seen in a number of other demonstrations. We force nitrogen gas into the container. That forces the liquid and some of the gas up into this pipe on the top, which has several dozen small holes in the top. The liquid and also some of the gas comes out, and it's very, very cold. Remember, 321 degrees below zero Fahrenheit, 196 below Celsius. When it comes in contact with the warm air, the water vapor in the air condenses into tiny droplets of liquid water, and that's what we call a cloud. And with that, I thank you all for coming.